So for this learning module, we'll look at the method of sections, which is an alternative way in which we can solve for the forces which are induced within members of a truss. So particularly, method of sections is more useful than method of joints if you are only interested in solving for the forces that are developed within a small number of members. If you were doing this type of problem in an actual from-scratch design, you can imagine enforcing equilibrium, and it would be particle equilibrium on every pin or joint in the truss, and that would allow you to solve for the force developed in each member, which would allow you to make the design decisions of how big the individual members should be. However, in certain back-of-the-envelope analysis situations, you may be interested in only determining the force developed in a few of the members, and this is when you would apply the method of sections. So it works a little bit different than the method of joints. What we're going to do is take the entire truss as an overall rigid body and segment it into two rigid bodies. And when we do that, we're actually going to cut some of the members in half. And we're going to model what really is our first look at the internal forces within a member. So up until now, we've been focused exclusively on external forces, even though I've drawn it up and drawn this, brought it up rather, and drawn this kind of diagram in some of the earlier learning modules. So what's happening is if a member is in compression, then any subsets of that method are in compression. So if I were to take and break that member into two, what must be going on is if I have the external forces, which are tending to compress the member, then there must be some internal forces such that segmenting this into two, the bottom member is actually compressing the top member in order to keep it together. What's going on is this member just isn't like collapsing, right? So each little part is not collapsing either. So the reason that it's not collapsing is the bottom part pushes back on the top part, and the top part pushes down on the bottom part. So an easier way to see that, do take kind of the time and go through and draw it out and make sure you understand why the forces are that way. But the way that I always think about it to keep it simple when I'm doing analysis is if an entire member is in compression, if I take any subsection of it, then the two subsections are also in compression. And the same thing holds for tension. One thing we should bring up, I think I've said this beforehand, but when you speak of members being in tension, you call those internal forces tensile forces. So just make sure that you know that when we do take the entire truss as a rigid body and we segment it into two separate rigid bodies, which will also be in equilibrium, that we're naturally going to be partitioning members of the truss, and we will need to describe the effect of that partitioning with these types of internal forces. The real advantage, the reason that this works better than the method of joints, if you only need to solve for a small number of sections, is when you take either subsection of the truss and analyze it as a rigid body, in the two-dimensional situation, you now have three equations of equilibrium. So when we analyze method of joints, under the assumption that all of the lines of action of the forces were concurrent, we just had two equations of equilibrium. They were just particles. But when we do method of sections, we're actually going to get three equations for each subsection of the truss, and that will allow us to solve for three unknowns. So if we can set it up in a way where when we do the partitioning, the resulting free body diagram of a subsection of the truss only has three unknowns, we're good. We can solve directly. So in terms of how that looks, say you had like a truss here on the bottom, and it has an external load applied at point A, 1,000 newtons in the downward direction. It has the reactions at D and E, but you were only interested in solving for the forces that would be developed in these three members, BC, GC, and GF. What you notice is if I actually draw a partition that would segment those three members, the resulting truss would be separated into two rigid bodies. Up here in the upper left figure, you see the portion of the rigid body on the left, and up here on the upper right, you see the portion of the rigid body on the right. And what we notice is that anytime we segment a member, for example, focus on member BC, what we have, and again, we're just assuming certain directions of these forces. If you remember when we did method of joints, we assumed that all of the members were in tension. And if the members were in tension, that meant that each pin or joint we were analyzing was pulled on by the member. In a similar vein, when we segment a member in method of sections, we're always going to represent the internal forces coming out of the member, which is an assumption that they're in tension. But the key thing that I want you to realize is when a member is segmented, for example, BC, notice that the internal tensile force FBC in the left portion of the free body diagram goes to the right, and in the right portion of the free body diagram goes to the left. And that's just a practical application of Newton's third law of the fact that reaction forces are equal and opposite. So hopefully you see how these free body diagrams were drawn as they are. It's basically all the external forces that you would have if you were analyzing the entire truss as a rigid body, namely the 1,000 Newton load and the three reactions. However, in addition, we do need to add on those internal forces, which we get by segmenting, and their directions are going to be determined by two things. We'll assume that each member is in tension, which means that the forces are going to kind of point out from the segmented bodies. And in the two resulting free body diagrams, the internal tensile forces will be equal and opposite. So it satisfies both of those conditions. So if you had to do a free body diagram equilibrium analysis, rigid body, of course, since these forces aren't concurrent, on either the diagram to the left or the diagram to the right, which one would you want to do? And hopefully when you look at that, you say, clearly, I want to do the one on the left, because the one on the right not only has those three unknown internal tensile forces that I'm interested in, the force in member BC, GC, and GF, but it also has three unknown reactions that I would need to solve. So even if I assume this is stationary, it's statically indeterminate. I have 6 unknowns and I only have 3 equations of equilibrium. However, this free body diagram on the left, there are only three unknowns corresponding to the tensile forces that I want in the members, so I can do an analysis and determine those directly. That's a statically determinate free body diagram. So part of the art of doing this well is you determine which forces you want the members in. You draw a partition that cuts those members apart. That's naturally going to produce 2 different chunks of a free body diagram. Draw in the internal forces as tensile forces going out of the cut members. Determine which of the two gives you the statically determinate situation. And here it's the subsection on the left, not on the right. And then just treat it like a problem from chapter 4. Now, the book actually goes into all of this detail and basically says, when you're doing the analysis, because remember, there are three linearly independent equilibrium conditions you can write. The 3 natural ones that we look at are that the sum of all forces in the x direction are 0, meaning that it doesn't translate left or right. Sum of all the forces in the y direction is 0, meaning that it doesn't translate up and down. And some rotational condition computed as the sum of all moments about a point must also be equal to 0. But those are just the 3 that you traditionally write. If you kind of go deeper down the road of theoretical mechanics, you'll see that another thing you could do is just write 3 equations of rotational equilibrium. But and the way to think about that is, remember, when you write your moment equilibrium equation, you're free to choose whatever point you compute the moments about. So there's an infinite amount of moment equations you could write. So what if you just wrote 3? Well, it will turn out if you pick 3 different points, the information that you get will include all of the information that's in the translational equilibrium equation. So what I'm trying to say here is, when someone asks you, well, what are the 3 equations of equilibrium? Well, there's the 3 we traditionally write. Sum of all forces in the x is 0, sum of all forces in the y is 0, and sum of all moments about some point is 0. However, a better way to say that is that they're, in general, for a planar 2-dimensional situation, you can only write 3 independent equations of equilibrium, because there's a bunch of them you can write, right? You can pick any point you want along the body and compute moments. But the resulting equations that you get are going to be what are known as linearly dependent. There's no new information in them. So the book emphasizes the importance of, when you're choosing your equilibrium equations, not only to try to make them essentially result in a system of linear equations, which is decoupled. So the book doesn't really do a good job of talking about this. And you have to remember, a lot of this text was written back in like the 20s or 30s, when having access to software, whether it's in a computer or in some type of calculator, that could solve systems of linear equations was hard to get access to. So you wanted to be careful in your approach to try to make your resulting linear system decoupled. That way you could, rather than view it as 3 equations and 3 unknowns, you could view it each as a system of 1 equation, 1 unknown, solve for that. Once you solve for that, substitute it into the second, and then that becomes 1 equation and 1 unknown. So it basically makes your underlying process much, much easier. So just to kind of show you an example of this, and I want to emphasize, you don't really need this to do this approach in order to solve these types of problems. It just makes it kind of more mathematically convenient, especially if you're doing it without a calculator around. So here is that subsection of the truss that we looked at earlier. And what the book is asking you is basically, which 3 equilibrium equations should you enforce? And in which order should you enforce them, such that each resulting equation only has one unknown, and you don't have to solve it as a system. Well, if you look at this, if I were to enforce rotational equilibrium about point C, meaning I were to sum all moments about point C, clearly I see this applied 1,000 Newton force is going to tend to induce counterclockwise rotation about point C. And for this to be in equilibrium, that must be counterbalanced by the clockwise rotation that FGF induces. Hopefully everyone has it by now. These two forces, FBC and FGC, won't contribute to any rotation about point C because their line of action passes through point C. So remember, the definition for computing the moment of a force about a point is you basically draw a position vector from the point to the line of action. Well, if the line of action goes through the point, that position vector is 0, so 0 cross anything is also 0. It's also just easy to see mechanically if you think about it. If a force goes through a point, it doesn't tend to rotate it about that point. It's totally translational. So if I enforce that the sum of all moments about point C must be equal to 0, that will directly give me a way to find for FGF. Next, if I enforce the fact that the sum of all forces in the vertical direction must be 0, what would that allow me to isolate? Well, notice that the only member that has the ability to counterbalance this 1,000 Newton force down is the y component of FGC. So if I solve for, if after enforcing the sum of all moments about point C equals 0, I'm able to solve for FGF. Then if I enforce that the sum of all forces in the vertical direction must be 0, I'll be able to sum for the FGC, assuming, again, we're making a little, the reason I was stumbling there is you're making an assumption that you have the adequate geometrical information in the problem, which we do in order to find the magnitude of that force, and you will. And then finally, if we enforce the fact that the sum of all forces in the x direction equals 0, even though FGC, the magnitude, and FGF will contribute to it because this has an x component and this is purely in the x direction, since we already know these, we'll be able to solve for FBC directly. So that's kind of what the book means by this sort of thing. What three equations could you write and what order would you solve them in order to get basically a one equation, one unknown scenario? If you sum all moments about point C, you'll get FGF directly. If you sum all forces in the y direction, you'll get FGC directly. Given those two pieces of information, if you sum all forces in the x direction, FBC will be the only remaining thing that you don't know. So hopefully that helps kind of emphasize the underlying principle of the method of sections. Just like the method of joints, it's a way to solve for the forces developed within members of a truss, but it's more useful if you're only interested in a subsection of the members within the truss. You just take your overall truss, you segment it into two sections, you draw in your internal forces under the assumption that all members are in tension, and you analyze whatever section of the truss that you segmented as a rigid body in equilibrium, which gives you three equations, and hopefully you only have three unknowns, and you'll have a statically determinate situation. I'm going to do the homework problem